Hello and welcome to this explainer brought to you by Forge College. I'm super excited to be your guide today as we explore a seriously fascinating chapter in the history of distributed systems. In our last lesson, Evolution of Practical Solutions, we explored those beautiful, pristine, theoretical concepts, voting, fault thresholds, and quorums. But today? Well, today we're leaving that perfect whiteboard behind. We're stepping right into the messy, unplugged cords, spilled coffee reality of early networks. Welcome to From Research to Practice in the Pre-Blockchain Era. Let's dive right in by comparing the frictionless world of mathematical proofs to the absolute rush-hour traffic reality of actual engineering prototypes. Because, let's be real, it's one thing to prove an algorithm works flawlessly on paper, but it's an entirely different beast to keep that same algorithm running when a physical server inevitably crashes, or, when a backhoe accidentally severs a fiber optic cable halfway across the world. Here's our quick roadmap for today. We'll be hitting theory meets messy reality, the lab versus the wild, fixing real-world problems, case studies in chaos, inside the replica loop, and finally, paving the way forward. Basically, we'll see exactly how early network chaos directly shaped the Web3 protocols we use right now.
All right, let's kick things off with Section 1, Theory meets Messy Reality.
So when researchers write proofs, they get to operate in these nice controlled vacuums. They rely on theoretical models like partial synchrony. Basically, this assumes that messages will eventually arrive, but acknowledges that the timing might fluctuate a bit unpredictably due to jitter or delay. It's a nice, neat, comforting mathematical assumption. But out in the real world, oh boy, engineers have to battle transient partitions, random disk stalls, and sudden process restarts. The math reassuringly says, hey, the message arrives eventually. But the systems engineer has to look at that and say, okay, sure, but when? And what exactly am I supposed to do if it doesn't?
Moving right along to Section 2, the lab versus the wild. Writing a mathematical proof really is like driving a sports car on a completely empty, perfectly paved track. Perfect crash semantics, synchronous delivery, totally reliable nodes. It's pristine theory. But deploying that code to a global network, that is the messy reality. Disk stalls, transient partitions, administrative errors. It's literally like trying to navigate rush-hour traffic during a blizzard, all while dealing with a flat tire. Every single assumption you made in the lab suddenly becomes a do-or-die design decision out in the wild.
Which brings us to Section 3, Fixing Real-World Problems.
Now, it's fascinating to see how these theoretical gaps mapped directly to some incredibly brilliant engineering mitigations. Take short network timeouts, for example. If your prototype assumes short timeouts are totally fine, your practical problem is that you'll get spurious leader changes the second the network lags even a tiny bit. The system just panics and fires the leader. The fix? Adaptive backoff. Or what about using in-memory state just because it's super fast? Well, the problem there is that a simple node restart means complete amnesia, total state loss. So engineers patch that by adding periodic, durable checkpoints to save progress. And this last one is absolutely my favorite. If you don't have replay protection, you get duplicate requests just clogging up the whole system. The mitigation was adding sequence numbers. It's quite literally using basic counting to prevent network ghosts from duplicating historical requests.
That perfectly sets up Section 4, Case Studies in Chaos.
So what actually happens when perfect code meets a deeply flawed network? It's absolutely a critical question we have to ask, because as we're about to see, a parameter that works flawlessly in a perfectly tuned, low-latency local test cluster can cause complete, cascading, systemic meltdowns when unleashed onto a global testbed.
Let's look at our first little mystery. We'll call it Case Study A, the bouncing leader. So, step 1, the system was validated in a low-latency lab environment. Everything looked great, right? But then, step 2, it gets deployed to the wild. Suddenly, global internet lag caused all these false timeouts. The system kept thinking the leader node had crashed just because its ping was a few milliseconds late, so it kept electing new leaders, over and over again in this crazy, continuous loop. Finally, step 3, the fix. Engineers had to implement adaptive moving averages for timeouts. It completely proved that a hard-coded timeout, which felt perfectly safe in the lab, is a dangerous liability in the real world.
Now for our second case, Case Study B, the cryptographic rollback. Step 1, engineers added strong, threshold-signed snapshots to mathematically guarantee the system's state. Sounds amazing, right? Totally bulletproof. But then, step 2, a human operator makes a mistake and decides to roll back a server configuration manually, which created a massive history conflict. Now, the cryptography successfully caught the error. It did its job, but ironically, the cryptography also completely broke the automated recovery system because the signed histories conflicted and the math just flat out refused to proceed. So step 3, a human-in-the-loop recovery checklist was required. It's such a brilliant reminder that high-tech, space-age mathematical proofs still occasionally require a tired human operator with a clipboard to sort things out.
All right, let's move to section 5, inside the replica loop. Instead of getting bogged down in complex Python or C++ code, just think of the anatomy of a replica like this. First up, you have sequence numbers for replay protection. They basically act like a tough club bouncer checking IDs, turning away any old or duplicated messages at the door. Second, persistent storage for durable checkpoints. This functions exactly like a save game file in a video game, making sure you don't lose all your hard-earned progress when the server's power inevitably goes out. And third, event loop timeouts for leader pings. Think of this as an incredibly impatient boss constantly tapping their watch, just ready to immediately fire the leader if they don't get a status ping exactly on time. The crucial takeaway here is that every single theoretical assumption ends up forcing a real-world design trade-off. Take a look at this. On one hand, we have synchronous disk flushes. This gives you incredibly high safety, guaranteeing that every single byte is saved, but it comes at the cost of high latency. It's super safe, but it's slow. On the other hand, we have batched saves. This gives you much faster speed by keeping things in memory, but if the system crashes before a batch is actually saved to the disk, you run a huge risk of losing progress. So engineers are just constantly out there walking a tightrope, trying to balance absolute safety against acceptable performance.
And that brings us to our final section, paving the way forward.
It's amazing to see how this enduring legacy built the foundation of our modern infrastructure. We're talking about explicit leader stabilization windows, checkpoint and truncate recovery, multi-party administrative protocols, and of course operational best practices. These seemingly minor duct tape fixes weren't just temporary patches, you know. They actually evolved into the absolute operational DNA of modern Web3 protocols. We quite literally would not have the blockchain stability we enjoy today without the early community documenting those exact prototype failures and collaborating on the fixes together.
Prototypes expose the boundary conditions that theory hides. I just love that quote. It perfectly captures our entire journey today. Engineering validation, which, let's be honest, really just means breaking things on purpose to see exactly how they fall apart in the real world, is just as vital, if not more so, than writing that initial mathematical proof. The theory tells you how a system should work, but the prototype? The prototype tells you how it actually works when things inevitably go wrong.
Building the future by learning from the past. Thank you so much for exploring this wild journey from the pristine research lab to chaotic reality with us. To dive deeper into these foundational Web3 concepts, and to get ready for our next lesson where we synthesize all these legacy design choices, be sure to visit us at forge.college. As we wrap up this explainer, I want to leave you with one final thought to ponder. When you look at the incredibly complex Web3 networks we rely on today, are the systems we're building right now secretly hiding their own theoretical boundary conditions, just waiting for the messy reality of tomorrow to strike? Keep exploring, stay curious, and I will see you in the next one.